And this would help in your problem set 2 as well. So problem set 1, one of your long questions is to calculate the efficiency of a 2-junction cell, right? So let's understand 1 junction first, and then I'll point you how to do a 2-junction, right? So what I'm using here is a Mathematica program that you have been given as a reference as well for your problem, and I'm using you can use any software you want. You can use MATLAB, Mathematica, Excel. I just like doing Mathematica for demos because it's a very real, if you change things, you see the result right away. So it's a good way to demo things. So let's see. So I take the temperature of the cell over here to be 300 Kelvin. Right? I give it the AM 1.5 spectrum as input. Right? And this is that AM 1.5 spectrum plotted out. And this is one of the reasons I like Mathematica. So if I make it 2, it will take the intensity of hopefully 2 cells. Right, so it plots it twice. Let's bring it back to 1. Okay, so this is the spectrum of my sun. Right, so it peaks somewhere around here, which is at a wavelength of 700 or 800 nanometer, but it has that shape of the black body. Right? Now, what I've done is what this person who actually wrote this program has done is he has calculated the number of photons above the band gap, just like we did. So you assume a cutoff function, a delta function, or a step absorption, function for absorption, and then you can plot the number of photons absorbed as a function of the band gap. So as you see, as you increase your band gap, right, you're absorbing less and less number of photons. So that is something that you pointed out, Dan pointed out as well. That the number of photons absorbed, that's the first term that I need in my to calculate my current as a function of the band gap. Now I can calculate the recombination rate. I'm going to use this formula, right? So I'm going to integrate this equation, which is my Planck's law, from energy equal to the band gap all the way till infinity. Right? And this is the equation for that. And then when I'm at the applied voltage, I'm going to just multiply this equation by the exponential function of voltage. So you can do all that, and you get this short circuit current as a function of the band gap. So again, you see, if you are increasing your band gap, you're getting a very low current because there are not enough available photons to get absorbed. But at the same time, your voltage or your VOC is getting increased because you're using a higher band gap material. So the voltage at which you collect your photons is going to increase. And this dotted pink line, this essentially gives the band gap. So this is at the band gap, this is just at a slope of 1. So you can see that this drop between the blue line and that dotted pink line is coming due to the recombination, right? So this dotted pink line would be that ideal case where my cell is at 0 Kelvin, right, where there's no recombination. In that case, my VOC or my open circuit current is in fact equal to my band gap. But if I'm at a finite temperature, I'll have some recombination, and that's why this VOC is falling as a function of the band gap. So now what I like the most about, so this is again that efficiency. So it's a product of my voltage into current, and you can see that maximum of around 33% coming in here. And the part I like the most is what these pie charts show. So okay, so let's compare the losses in a cell which has a band gap of 0.5 eV. So if I have a band gap of 0.5 eV, right, I have very few photons below the band gap. So this pink slice is the number of photons below the band gap. So that slice is very small, right? All these other photons have energy which is excess in the band gap, right? So all these other ones, I'm extracting out of them, but I'm going to extract them at a very low efficiency because they have much higher energy than the band gap. So I'm extracting them at a band gap, at an energy which is equal to the band gap, right? And this green pie over here, this gives me the recombination, right? So if I have a lower, let's say I have two cells, one is higher band gap, one is lower band gap, which would have more recombination? Okay, the reason? Okay, so Pranav is answering it from a semiconductor point of view, right? That if the band gap is low, then you have more recombination, right? But this is not getting to semiconductors. Besides that, no, yeah. Yeah. Yeah, so we can just think of it in terms of Planck's law. So cell which is lower band gap is going to absorb everything which comes in, above that energy, which is low, and that's why it's going to its emissivity is going to be higher as well. So one way is to think about it is from the band gap, the other way is just from Planck's law. So if I compare it then again to a case which a cell which has 1 eV band gap, the number of photons which are below the band gap, that slice has increased, and the number of photons which have excess energy, that slice has kind of decreased, right? But and you see if that green slice, that has kind of decreased as well, because I'm increasing my band gap. Yeah.
So why are you saying that
they're still useful, but they're being used at a lower efficiency. Right? Yeah. So over here is showing for the case of 2 volts. So again, the number of photons which are below the gap, that pink slice has further increased. The number of photons which are beyond the band gap has squeezed out, and that recombination which was that green slice has squeezed out as well, because I'm using a higher band gap material, so there's way less radiative recombination happening as well. Right? Is that clear? This program is available for you guys to do your problem set as well.